Hey guys, my name is Sagar Batani and I'm shooting this video, exam wrapper for Professor Kim's class, Physics 2212 Modern. So the problem we're looking over is problem 3 from test 1. So you can see that we got this diagram up in the top of the page, and the first part of the question says, determine an expression for the charge on a slice of the rod, delta Q, in terms of the infinitesimal length delta X of the slice. So we know that doing this that you need to find the linear charge density first, which in this case for a rod, as we know, is going to be Q over L. And as in the given in the problem, the actual charge is negative Q, so it'll be negative Q over L. Then, since we know that the linear charge is negative Q over L, we know that delta Q is equal to linear charge times whatever we're in respect to, which is delta X in this case. So our delta Q would equal negative Q over L delta X, so that one's pretty straightforward. Moving on to part B, you're supposed to sketch the relative position vector R observational minus R source for an arbitrary slice of the rod delta Q. Sketch the direction of the electric field delta E due to delta Q at the observation location marked X. So for this, we can actually just go through the relative position. So we know that our relative position is going to be observation location minus source. We know our source is X, 0, 0. And our observation is L plus A, B, 0. So we pretty much just subtract those two vectors, and we get our R equal to L plus A minus X, B, 0. Excuse me. Moving on to part C, we have to derive an expression for the vector electric field delta E of the slice of the rod at the observation location marked X. So we know that delta E is equal to 1 over 4 pi epsilon naught times delta Q, which we found in part A, all over R, the magnitude of R squared, times R hat. And pretty much since R hat equals R vector over R magnitude, we can actually make that 1 over 4 pi epsilon naught delta Q over R magnitude cubed times the position vector found in part B. So when we plug in for this, we know that delta Q is equal to negative Q over L, as we found in part A. The delta X is something we still got to take respect to. 1 over 4 pi epsilon naught is just a constant. It's equal to 90 to the 9th approximately. For the magnitude, we know that we had to take the magnitude that we found from part B, which was that R vector. And so when we do that, we get L minus X plus A squared plus B squared. And that's all actually raised to the 3/2 because we take into account the R hat as well. And when we take into account the R hat, that leaves us with the R magnitude vector left. I'm sorry, just the R vector in general left. Which is L minus X plus A, B, 0. So that's our expression for the vector electric field. And then we had one more part to this problem. That's right here. And it's part D, and it says, set up but don't solve the integral required to determine the electric field at the observation location X. So we can see that when you're setting this up, what we're looking at is that since the last thing was DE, and we have to integrate this, we're going to be solving for E. So the first thing we need to figure out is our limits of integration. Looking at that drawing from before, we know that it's just going to be from 0 to L because it's pretty much just given. That's just the way that the rod's going to rotate. But then you have to integrate the expression, which is 1 over 4 pi epsilon naught. So that's a constant. So as we know, constants are really never going to integrate. But we don't even have to solve this one, so we can just go through this. So it's the limits of integration would be L and 0, and then you'd have to integrate 1 over 4 pi epsilon naught negative Q over L dx all over that magnitude raised to 3/2, and then times that R vector. So pretty much what we got in part D, we just got to integrate that. And yeah, so that's that problem. Pretty straightforward. Thanks for watching, guys, and have a good one.